Okay, please. Okay. Sorry for late start. We're ready. Okay. And yeah, so any question from this time? This time was quite definition heavy. So we talk about this linear constant coefficient equation. And I guess one thing to emphasize again is that, well, it specifies a system, but it's not necessarily an LTI system because the system is not totally specified by the differential equation. To specify the system, you need to specify the auxiliary conditions, and only when you pick a particular, a very well picked auxiliary condition, your system will be LTI. And here we have shown that one of the conditions emphasized that is the initial rest condition here. Okay, and yeah, we show that if you pick an initial rest condition, then this linear constant coefficient differential equation, they are not only LTI, they also are causal. Okay, so it's a very nice condition. Okay, here we finish this time with this proof that if we have those linear constant coefficient differential equation, and if you pick its auxiliary condition as initial rest, then the system is indeed LTI and also causal. And I guess let's go back a little bit. Here is an initial rest condition. Again, initial rest means that the output is 0 until your x is not 0. And it's important to emphasize a little bit here that it's important to emphasize that this is not the initial condition. Okay? It's initial rest. It's not that your system is 0 at some fixed point. It says, so if we actually use this, we see that initial rest means that your system is 0, and always order, and a lot of its derivatives are 0, at a point where your x of t start being non-zero. Okay, so this is a kind of a weird condition, but we think it's very physical, and we'll use it. Okay, and yes, and we also see that for differential equation, usually there are a lot of solutions. So we can solve it without the auxiliary condition first, and the solution will be a particular solution plus a homogeneous solution. And then we'll use our initial rest condition or other auxiliary condition to determine what's the appropriate homogeneous solution you will pick. And so we see in this example of dy dt plus 2i of t equal to x of t, we solve for that. This solution is in this form of a e to the minus 2t plus k over phi e to the 3t, where this a e to the minus 2t is a homogeneous solution, and you can have any multiple of a here. And we see the initial rest condition, and you determine that what is a, and a is k over 5. Okay. So that's the linear constant coefficient differential equation. And today we are trying to finish chapter 2, and hopefully you can go into chapter 3 a little bit. Okay, so we'll skip quite a few over this slide. But first, let's go into the discrete counterpart of the differential equation. That's a difference equation. Okay, so difference equations equation look like this. So we jump straight forward into this very mathematical form. Okay, so you see that, well, it's a lot like a differential equation, except that instead of a derivative of y of t and a derivative of x of t, we have those y of n and x of n that just shifted. Okay, so the difference is, I think it's a bit intuitive why this corresponds to differential. Okay, because differential is kind of slow, but here, well, for whatever reason, it's just defined this way. So it's just a time delay signal. Okay, so you just have y of n delayed by some k and x of n delayed by some k, and k can be some 0 from n and 0 from m here, and that just depends on how many order you want your equation to be. Okay, and but anyway, just like in the differential equation case, in the difference equation case, your solution is also going to be written as some particular solution plus homogeneous solution, and the homogeneous solution is the solution to this homogeneous equation where you just keep the y of n part, and you say the x of n to 0, so you just say this is a linear combination of of y of n is 0. Okay, so summation. Okay, and anyway, so this is difference equation, and it turns out difference equation is oh, sorry, and let's talk about auxiliary condition. Okay, and so difference equation, you also need a lot of auxiliary conditions, and the number you need is kind of same as in differential equation. So it depends on this big N. So if you are delaying your y of n by some big N, then you need a big N different auxiliary condition. And here we also pick initial rest, and initial rest means that if x of n equals 0 until some point n0, then your y of n is also 0 until this n0. And this means that there are a lot of 0 before this n0 for y of n. And what we really need to solve for those things that after n0 is that you need big N of those points are 0. So you need y of n0 minus 1 equals 0, so this point is 0, and y of n0 minus 2 equals 0, etc. And yeah, so you need the previous big N points equal to 0. And if you have those, then you can solve y of n, and will not prove again, but I think it's pretty straightforward to show that the system will be causal and real TI. Okay. So yeah, and this is a system we consider for now. So we have a linear constant coefficient difference equation, and with initial rest. Initial rest means that y of n is O0 before this n0 point where you start have x of n on 0. Okay, and I guess this is a little different from the continuous case. Is that discrete case is easier in the sense that there is a quite straightforward way to solve the difference equation. Is you can just rearrange your equation and write down this recursive formula. Okay, so let's go back a little bit. So our formula is this: is a summation of a whole bunch of y of n and y of n minus 1, y of n minus 2, all the way to y of n minus k. And you just move everything around and leave just y of n here, because there is going to be, so for the k equal to 0 term, it's going to be a0 y of n. Okay, so if you move everything to the other side, then you have y of n equal to this 1 over a0 and your summation of x and all the other term of y. Okay? And okay, so assuming a0 not equal to 0, then this is a very explicit way to, this give you a very explicit way to calculate y of n. And yeah, so for those of you that's computer science is in the computer science department, you know that you can write a recursive program for this thing. So basically, you want to calculate y of n, then you look for a few points, because all those y of n minus k are points before this n point, right? And so you look back at those y of n minus k, and then you can calculate y of n. Okay. And yeah, you look back at those y of n minus k and those of n minus k, you can just calculate, because x of n is given. Okay. And but you will say you don't know what is y of n minus k, so you keep looking forward. And you're looking forward, and when does this end? That's why initial rest is being useful. So say you look at this point, then you need to look at those 4 points. Then you want to calculate those 4 points you look at it before. But if you want to just calculate this y of n0 point, then you know that all the previous point you have y equal to 0. And so all the y equal to 0, you only need to calculate x, and x are probably also 0, etc. Okay. And I guess as one of the example, no, this is another thing. Okay, so this is a recursive formula, and also a special example of the case where big N equal to 0, then you have very explicit formula for this. So if big N equals 0, then you don't even have those recursive y over minus k term. Then you don't even have those y of n minus k term, then your y of n is just this linear combination of x of n minus k for some points before this n. Okay, and say you can calculate the impulse response, and you will have your h of n look like this. It's bn minus a0 for n between 0 and big M. Big M is big M here, and then 0 otherwise. Okay, you can calculate that pretty easy. Okay, and I guess let's see one of the example for this recursive formula. Is like one of the easiest recursion, so it has one level of recursion. So we have y of n minus 1/2 y of n minus 1 equal to x of n. Okay? And we try to see how this difference equation will have your y of n. Oh, sorry. There is need to change this a little bit. Okay, sorry. So we try to see this example and see how this recursion goes. And as we say, basically what we want to do is we want to keep our y of n on your left hand side and throw everything away to the right hand side. Okay, so you see you can calculate y of n from x of n and y of n minus 1, and you always know x of n because it's some given thing. And basically you need to calculate y of n, and you need to go calculate y of n minus 1, and for y of n minus 2, you need to go y of n minus 2, etc. And then we suppose we have an initial rest, and we consider basically like an impulse response. So we think our x of n equal to k delta of n. So it's just a spike of height k at n equal to 0. And then by initial rest, we know that for all the n less than n0, n less than 0, y of n equal to 0. So we only need to calculate y of n for n greater than 0. And then we calculate y of 0, start from calculating y of 0. Then you see y of 0 is x of 0, which equals to this k, plus 1/2 y of minus 1. And from initial rest, we know y of minus 1 equal to 0. So this is just x of 0 equal to k. And then y of 1. So we start building this recursion from this n0 where x of 1 being non-zero, and then y of 1. Then now we know y of 0, we can build on y of 1. Then y of 1 equal to x of 1, which equals 0 because x is 0 everywhere except for n equals 0. So y of 1 equal to x of 1 equals 0, and plus 1/2 y of 0. And y of 0 was k, so this is 1/2 k. And now we know y1, we can calculate y2, so y2 will be 1/2 of this y1, it's 1/2 square k. And so you see that this recursion gives you that y of n equal to 1/2 to the nk. And here is the example. And then we can also calculate the impulse response of this system because we basically already calculated. This is a generalization of impulse response. If you just say k equals to 1, then x of n will equal to delta of n, and we see the impulse response will be 1/2 to the n for n greater or equal to 0, and to say it's 0 for n less than 0, and we just put u of n here. Okay. And so that's a difference equation. It's very similar to differential equation, except instead of differentiation, we have this time delay, time shift, and we see that it can be solved by this recursive formula, or calculate with this recursive form. Okay, and if there is no question, then let's go to a topic that's a little related to differential equation and the difference equation. That's those block diagram. And so we talk about those block diagram to express our system. We kind of skip over the fact that there can be a loop in our block diagram. And here we see that having these feedback loops are a very nice feature because they can be used to express a differential or difference equation. Okay, and so So, for example, I think it's a bit easier to understand if you think about discrete case. Okay, so you think about we have a discrete time difference equation like this. So y of n plus ay over minus 1 equal to bx of n. And then we can write this equation into just as we say, we can write into a recursive form. So we put y of n still here and then move everything other side. So you just have this ay over minus 1 become minus ay over minus 1. Okay, so y of n equal to minus ay over minus 1 plus bx of n. And we find out that if we want a system that has this kind of response, then we can build it up with the block diagram like this. Okay? So this block diagram basically have three elements. You have this addition element that we told before. So this addition element have one input and so one input, two input, and the output is just a summation of those two input. And then we also have element that's a straight line with a number here. Just means that so this is actually a system, but it's a straight multiplying system. Amplifying system it means that whatever input we just output with multiplication of a. And then we have a more interesting system here. We have a time delay system. Okay, so we have a signal x of n here, and then we say we can have a time delay block that output the same signal but delay with the time x of minus 1. And then we see that if we put a feedback loop like this, then this block diagram, if you control a block diagram like this, then this block diagram will have output y of n that's related to input x of n, just like this equation. Because so the big 2 points are I think here and here. So here we have a branching. So the output is y of n, and so this branch here is still y of n, and then this y of n will get delayed to be y of n minus 1. Then you multiply by minus a. So here at this addition you are adding bx of n plus minus a y over minus 1. So you see that at this addition here, y of n equal to minus a y over minus 1 plus bx of n. Okay, and yeah, so you see that I think this goes two ways. So one way to see this result is that, well, you see that you can express a difference equation as a block diagram. Okay, but I guess more the more useful way to see this is the other way around. I guess a similar and I'm not sure it's the same direction, the opposite direction. But I guess another way to see this is that if you want to construct a system that has this property, then as an engineer, then you know that you want a system with this property, then you can just look into build a system with these three kind of elements. So if you can build some system that will do this time delay, some system that do this multiplication, and some system that do this addition, and they just piece those elements together into this feedback loop. Then you know that if you run this feedback loop, then your input and output will satisfy this relationship. Okay, so I guess like as an electrical engineer, you know that you want to build a system satisfied by this differential equation. Then you can build a system with this feedback loop, and this system will represent your difference equation like here. Okay, and so this is a discrete case. Any questions so far? Okay. I think the discrete case is a bit more straightforward. And anyway, then let's go to the continuous case. And at the face value, the continuous case is very similar. Okay, so say we want to build a differential equation like this. So it's a lot like a differential equation that we just solved at the very beginning over this section. So dy dt plus ay of t equal to bx of t. And so you want to do kind of a similar strategy. So you put y of t on one side and move everything to the other side. So you y of t here and then move this dy dt to the other side and divide everything by a. So you have minus 1 over a dy dt plus b over x of t. Excuse me. Okay, and so you see that you want a similar element. So you have this addition element that will do this addition here, and then you have this multiplication element that will change all the coefficient here. And then the other element you want is you want dy dt here. So you want the differentiator. So you want something that input x of t and output dx of dt. Okay, and then the build-up is basically the same. So you have split y of t here. I guess another element is then you need a splitting element. Okay, that's kind of implicit. But anyway, so you have y of t here, they split it, and you go through differentiator, it becomes dy dt, you multiply by minus 1 over, it becomes minus 1 over dy dt just like here. And yeah, then you add back to this b over x of t, then this feedback loop will give you this differential equation, because y of t, this line here will equal to b over x of t plus 1 over a dy dt. Okay. And yeah, so this plot diagram will represent your differential equation here. And but there is a bit more thing in the a bit more issue in the Han-Hsuan case. The issue here is that the differentiator is hard to build. Okay, it turns out yeah, differentiator is usually very hard to implement and unstable. And so you don't really want a differentiator in your system, and so instead you want the integrator. Integrator are easier to build. I think intuitively, just thinking about doing integration is more stable operation, because you basically just add up all the previous signal. Whereas for the differentiator, you need a very tiny sampling of your yeah, you are basically taking the slope of your input, and yeah, it's very sensitive to the time step you take to your signal. But anyway, I think here we can take that differentiator is hard to implement for now. And so instead we write this as an integrative form. So we write dy dt equal to, so we put the dy dt on the one side and have everything on the other side. Okay, bx of t minus ay of t. Okay, and then here we kind of assuming initial rate, so we assume y minus infinity equal to 0, and and then we integrate both sides. Okay, and yeah, so we integrate both sides, and then this side become y of t. And the other side is the integration of bx to t minus ay of t. Sorry, now it's off top because the t is the upper bound here. Okay, and yeah, so instead of this this feedback loop, we want to run our system with this feedback loop, and let's check that this is the same as this equation. Okay. So so the output is y of t, and there will be integration of the summation of two things. So it's minus ay of t and minus a, and minus ay, and then plus bx. So this line here is minus ay plus bx, and it got integrated and it become y of t. Okay. And yeah, so this feedback loop will implement this system. System with this equation. And yeah, so any questions so far? If not, then yeah, I guess a few closing comments. And so first comment is something that will probably confuse you. Then you can think about how the auxiliary conditions are fitting into those equations, because here we only talk about the differential equation part. And another thing to confuse you about, and which we will actually talk about later, is that here we only have first order system. Okay, so here you see you only have one order of dy dt and one order of this time delay. And then you can think about how we write the block diagram for higher order equation, and that's something that we'll cover in the later part of the course. Okay. And but for now, this is just an introduction to show you that differential equation and the difference equation can be expressed by a feedback loop feedback system, and in terms of engineering, that means that you can build a feedback system and they will express your differential or difference equation. Okay. If there is no other question, then let's go to a different topic. Okay. I guess this is kind of application of our analysis of the TI system is that we can define some sigularity functions that they are basically integral and derivatives of delta function. Okay. I guess this is a very mathematical application and also will be useful in it's kind of a back and forth. These are derived from our analysis of a TI system, and they also help us to do further analysis of a TI system. Okay. And anyway, first we go back to talk about to give more analysis on unit impulse. Okay, so so I guess this whole chapter is about continuous time case. So this is nothing to do with discrete time case, because the discrete time case the unit impulse function is just very simple. Okay, but in the continuous case, the unit impulse this delta function is a very weird function, and we will get a little bit of analysis here by our analysis with a TI system. Okay, and so our first analysis is a result that we already get. Okay, and the result we get is x of t equal to x of t convoluted with delta of t for every x of t. We got this result before by analyzing the system that's an identity system. We said that your system is an identity system, then y of t equal to x of t, then if your x of t equal to delta of t, then y of t, which is equal to your h of t, will also equal to delta of t. Then your y of t, which is also equal to x of t, then will just equal to x of t convoluted with h of t equal to delta of t. And here we get another derivation of this property from kind of a straightforward derivation from our property in the delta function. So in chapter 1, we have the sampling property says that the delta function will sample your any function at some point. So you put your delta function at point t0, then you will sample this x of t0. Then you just integrate both sides. So here nothing really happens. You integrate both sides. So you integrate both sides from minus infinity to plus infinity. Then this side you write it as integration. Then the other side, because x of t0 is just some number, so you just say x of t0. Then you integrate delta function, then it becomes 1. So this side becomes the x of 0. Then you do a whole bunch of change of variable, and note that delta function is an even function, so delta of t minus t0 equals delta of t0 minus t. And yeah, then you find out that your x of t then you do this change of variable, then this is a bit of too much change. Okay, so you do change of variables a lot, so t0 becomes t, so this x of t0 becomes x of t, and this integration will turn into a form of convolution between x of tau and the delta of t. Sorry, x of t and the delta of t. So x of t and the delta of t. And so this is called the shifting property of unit impulse. So x of t equal to x of t convoluted with delta of t. And also you can do some time shift here, and you see that x of t minus t0 equal to x of t convoluted with delta of t minus t0. Okay, so this is a very nice property to remember. Okay, x of t equal to x of t convoluted with delta of t. And then we also see that from here, then you see that if you convoluted delta of t with delta of t, so basically you change x to delta, then obviously that should also get back to delta of t. So delta of t equal to delta of t convoluted with delta of t. And also you can do this more times, so you convolute delta of t 3 times, you should also go back to delta of t. Okay. And so those two by itself are pretty interesting property to know. And then you can kind of go backward to get a bit of intuition on delta of t. So before we kind of say that, I guess we go back to the definition of delta of t a little bit. So we say delta of t is this function taking this delta sub triangle function taking limit to triangle go to 0. So it's rectangular with height 1 of a triangle and with triangle and taking limit of a triangle go to 0. Okay, and so if we kind of do a bit of touring around, so from this equation, and we think, I guess, okay, so this is a bit of going around. Okay, so we think about this triangle function, and we take its convolution, and you do a bit of calculation. You see that the convolution of two of those rectangular function become a triangle function. It's a triangle function with width 2 triangle and height 1 over triangle. And we call this function R sub triangle. And by this equation, then we see that when we take a triangle go to 0 for this equation, then those two of delta sub triangle go to delta function. And we see that so those rectangular subtriangle function go to delta function, and we also see this triangle function. Okay, so two major triangle in my words, in my sentence here, but this R sub triangle function, when they go to 0, when triangle goes to 0, it should also become delta function because we know delta function convoluted with delta function should equal to delta function from here. And so we see that there are different functions that when you take the limit of triangle go to 0, they become a delta function. Actually, there are a lot of them. So, for example, you convolute this function with this rectangular function again, then it's also another function that's very narrowly shaped, and then will go to the delta function when triangle goes to 0. Okay, and yeah, so there are many parameterized functions. Where you take a limit, they become a delta function. Okay, and we say those functions behave like a unit impulse in a limit. And another function that we don't say in the word here, but I can draw here is that I think you can try to show it yourself. That if instead of placing your delta triangle from 0 to plus triangle, you can also place it you can do a time reversal, so you place it on the other side. So it's a triangle, so it's a rectangular from minus triangle to 0. So this function also, when you take the triangle go to 0 limit, it should become the delta function, and that's how you prove this thing. So delta function is even function in a very more rigorous sense. Okay. And anyway, so many functions that will behave as a delta function when you take a limit of this triangle parameter go to 0. Okay, and we can also analyze this behavior a little more, and so we can think about. I guess this is useful when you try to build an approximation of delta function. So you want to build a pulse that behaves like a delta function. Then you want to see how short your pulse should be for your function to really behave like a unit impulse. Then you can test it on the system that you want to hit with. So say you want to hit the system with the unit impulse, and you want to see whether the response is like the unit impulse response. Okay. So say you consider you hit the system, this system divided t plus 2 of t equal to xt with one of those functions with different triangle. Okay, and they want to see when does this look like this x of t equal to delta of t. Okay, So we hit with different this delta sub-triangle and the R sub-triangle. And so here are plot of the result. Okay, so we see different result, and then you see that as the triangle go to smaller and smaller, then this delayed peak goes closer to zero, and you kind of feel like when your triangle goes to very close to zero, then you have this exponential decay response. And this is independent of whether you hit with this delta sub-triangle or R sub-triangle. Okay? So delta sub-triangle look like this, and R sub-triangle look like this. And you see that when your triangle is quite finite value, then the response looks kind of a similar shape, but not totally, because you see this is smoother at the top, and you have kind of a sharp edge here, etc. But as the triangle goes to zero, they all converge to this impulse response. Okay, and then here we hit it with a more different thing. So here we hit it with this basically three convolution with delta sub-triangle. So this delta sub-triangle convoluted with R sub-triangle, etc. And then we even have a fourth order convolution here. Okay. And it's an even smoother function when triangle is non-zero, but they all converge to this exponential decay function. And here we just show the result. So this exponential decay function, actually the function HOT, when we calculate, it should be e to the minus. Okay, so here is very small. Let me write this in a larger form. So let me write it here a bit larger. So it's e to the minus 2t u of t. Okay, this is h of t, and it looks like this. It's an exponential decay function. And we see that so every approximation of our delta function, when we take this triangle equal to zero, they converge to this h of t equal to e to the minus 2t u of t. Okay, and also one interesting thing to think about is so how small this triangle needs to be for it to be look a lot very like this h of t. Okay, so here we see that the triangle is 0.0025 is enough, but y is around 0.0025. And it turns out that this triangle is small enough depend on the parameter of the system. And for example, so the system before was adding 2y here, and if you add 20y here, then the system will need a smaller triangle to feel like actually impulse. So yeah, basically the time scale of the system will depend on the different coefficient here. But anyway, in terms of pure mathematics and I guess in terms of calculus, we are always taking the limit of triangle go to zero, and the coefficients here are constant, so we can always be small enough to take the triangle go to zero. Okay, so yeah, so that's some property of the delta function. I guess very direct use is that delta function convoluted with itself, still delta function, and also basically anything that has area 1 and that has width goes to 0 will become a delta function when your width goes to 0. Okay, and so that's delta function, and okay, then there's more about delta function. Okay, and now we go to really mathematical, and I think we can skip a bit of this, but let me just say the high level. So high level is that in terms of mathematics, we define delta function before as well. We define delta function as this limit of this delta triangle function taking limit of triangle to 0, and there is kind of more elegant way to define delta function is that you can just define delta function in terms of its convolution. Okay, so you can also define delta function as a function that convolute with anything will get back to the same thing. Okay, and yeah, and we call this operational definition of delta function because this is seen as operation on other function. Okay. So this is the operational definition of delta function, and then you can do some mathematics to show that this operation definition can give us all our property we know about delta function. Okay, so for example, we can derive that delta function you multiply another function and then integrate it, and you will become the function at 0. Okay, so this is kind of like the okay. So now it's like a sampling property integrated. Okay, so it's integrated sampling property at t0 equals 0. Because remember, the sampling property was this, so x of t times delta of t minus t0 equal to x of t0 then delta of t minus t0. Okay, so from this operational definition, you can basically get back the sampling property, and yeah, and then you can also go the other way. Okay, so the other way we already see. So okay, so this is like a weaker sampling property. So this is weaker sampling property 2.139 is a sampling property only at t equal to t0 equal to 0. And from here you can also derive our operational definition. So yeah, from this property, then you can also derive that x of t equal to x of t convoluted with delta of t. Okay. And yeah, the calculation here a whole bunch of changeable variables. So I think if you want to check it out, you can check it out yourself. Okay. But the high level mathematics is just say that you can have a different definition of delta function. So you have this definition and this definition, they are the same. Yeah. And yeah. And we can also derive more property from our definitions. So from this 15 definition 2.139, we can derive that divide back to our sampling property. So this was an integrated form, and we can go back to our sampling property, says that the f of t times delta of t equal to f of 0 times delta of t. Okay. Yeah, so this just tells you that you can have several different definitions of delta function, and anyway, so those definitions are all equivalent, and you can think of these as a fundamental definition of delta function. Okay, and I guess let's go to a bit more interesting. So instead of delta function, then let's define a new function. Now let's define this u1 of t, which is the unit doublet. Okay, so now we are going to play with the derivative of delta function. And now this is something very weird. This is something more singular, kind of more singular than delta function, because you think about delta function, it already has infinite height. Then how you define its derivative is going to be very infinite. Okay, you cannot even draw a slope over a delta function. But nonetheless, we see that there is a very interesting way to define this derivative of delta function is you consider the analysis of LTI system. So you consider analysis of this LTI system as y of t equal to dx dt. Okay, this is LTI system. So this is a very well defined system. So it's a differential equation with n equals 0, because big N equals 0, you don't need any auxiliary condition. And also you can just look at this equation and see that you give me x of t, then I can calculate y of t and any t. Okay, and this system is indeed LTI. You can check it yourself very easy. It's linear, and also you do time delay here, then you also get time delay here, because dt equal to dt minus t0. Okay, so this system is LTI, and then we use the fact that this system is LTI, then this system can be characterized by its impulse response. So this is a thing that we learn a lot about. Basically, the thing we learn most about the most important thing we learn in this chapter is that you analyze LTI system, you regulate its impulse response. Okay, so you think about what's the impulse response of this system. So this h of t equal to d delta dt. Okay, and is a response to delta function that is y of t obviously equal to d delta dt. And just as we said, this d delta dt is something very singular. But nonetheless, we can just define it as something and give it a name, so we call it u1 of t. So the u sub 1 of t is d delta dt, and we know that it's impulse response to the system of y equal to dx dt. This is a derivative system. And then now from this LTI system analysis, we get something very interesting about this u1 of t, being that so we think about this system. So output y of t equal to dx dt just by the definition of LTI of the system. And we know the system is LTI, so y of t should also equal to x convoluted with the impulse response h of t. And we know h of t equal to u1 of t. Okay. And then those things are all equal, so we see that dx dt equal to x of t convoluted with u1 of t. And this should be set true for every x of t. Okay. And so we get something very interesting. We see that you want to do derivative. One way to do derivative is by actually doing convolution. Convolution with this very weird function d delta dt. Okay. And so this is a unit doublet. We have that for any function x of t dx dt actually equal to x of t convoluted with this u1 of t, which is equal to d delta dt. This is a property we get from our analysis of LTI system. Okay, and I think it's a good time to break. And let's leave it here to let you think about the real break. Okay, let's take a 10-minute break.这边怎么说？就是说 delta of t 是个 integrate 起来是 finite value 的 function， 但是它 function 本身的 value 是没有 bounded 的嘛，因为它有无限大的部分。在零的时候它是无限的。对。我懂。 Hello. Okay, let's get back. And yeah. So this is our first singularity function. It's the derivative of unit impulse function, derivative of the delta function, and we see that it has this interesting property that we can express derivative of any signal with it. So dx dt equal to x of t convoluted with u1 of t. U1 of t. Okay, so we have that, and then similarly we can do this even more. So we can do the same thing for second derivative. So we have that. So we think about this system that y of t equal to d square x of t dt square. Okay. And so this system will, once again, this is LTI, so it's equal to x of t convoluted with the h of t, which we will write as u2 of t, and just like before, this u2 of t will just be the second derivative of your delta of t. So u2 of t will be the delta of t dt squared. Okay, and yeah, we see that for any system, for any signal, x of t, then x of t, the x of d square x of t dc square equal to x of t convoluted with u2 of t, where u2 of t equal to d square delta dt square. And there is even something more interesting happening here is that so there are different definitions of u2 of t. Okay. That's because we know the second derivative is just you take the first derivative twice. Okay, so d square x of t dt square equal to dx dt. Then you just do dt again, and you know when you do dx dt that equal to x convoluted with u1, and you do differential again that equal to convoluted with u1 again. Okay. And then now we use you compare this system and this system, and then this LTI system and this equation and this equation. Then you see that u1 is equal to u2 will be equal to u1 convoluted with u1, and I guess here we use a little bit of the associative property of the convolution. So yeah, so u1 convoluted with u1 equal to u2. Okay, yeah, and so you see that this double derivative of delta function was actually equal to the first derivative of delta function and then convoluted with itself twice. Okay, so that's very interesting. So u2 of t equal to defined as d square delta of t dt square is actually also equal to u1 convoluted to u1, and and we know that x of t convoluted to u2 of t equal to d square x of t dt square. And then you can think about you can do this k times, so just keep generalizing to the higher order derivative, and then you see that uk of t will equal to u1 of t convoluted with itself k times, and x of t convoluted with uk of t will be the case order derivative of x of t. Okay, so those are the sigularity functions. They are the derivative of delta function. And here we try to get a bit more intuition about just u1 of t, the unit doublet. Okay, this u1 of t give you derivative. Okay, and u1 of t is ddt delta of t, and it gives us that dx dt equal to x of t convoluted with u1 of t. And here we try to give a bit of intuition about what the u1 of t should look like. Overall, we only have this very abstract definition of u1 of t being d delta dt. And so we try to plot this function, and as it says, it's going to be very similar. Very singular. So we start with the delta subtriangle. So we said this delta of t was the limit of this delta subtriangle taking the limit of triangle go to 0. Okay, so delta triangle is this rectangular function with height 1 triangle with the triangle. And then we think about taking derivative of those things. Okay, and then we see that even where triangle is non-zero, this the delta triangle dt function is already singular because you have a step of 1 triangle here. So when you take a derivative, then you have a delta function of height 1 triangle here. And then at this triangle point, you have a delta function of minus 1 triangle here. Okay? So even when triangle is not equal to 0, this U1, this triangle approximation of U1 is already singular, and it's a spike at 0, and it's a positive infinite spike at 0, and a negative infinite spike at the triangle. And anyway, and so that's that. So you write it in mathematical form. It's 1 triangle of delta of t. So this thing minus the delta of t minus triangle. So it's this spike. Okay. And then we can think about what if you do convolution of x over t with this thing. Okay. Then you actually get a nice result. Okay. So you think about this function and you take a convolution of any function x over t with this, and then because we know that x over t convoluted with delta function, just give back x over t, and x over t convoluted with delta of t minus t0 get to give us x over t minus t0. This is time shift, the time delay system we talked before, or time shift system we talked before. Okay. And yeah, so if you have x over t convoluted with this thing, then you do the linearity of the convolution, then you have 1 triangle from this thing. Then x over t convoluted with delta of t get back to x over t. X over t convoluted with the delta of t minus triangle give you us x of t minus triangle. So this is x over t minus x over t minus delta. So this is excuse me. This is dx dt. Okay. Yeah. Yeah. So this is a difference of x, and divided by some infinitesimal in time. So this is like a dx dt. So we see that this is a very weird singular function. It intuitively gives us this derivative behavior because you convolute the function x over t with this, it gives you back dx dt. Okay, and yeah, and then so this is like a more straightforward definition of our u1 of t, and but in fact, just like in delta of t, we say the delta function, we can give it an operational definition by just saying x of t equal to x of t convoluted with the delta of t. And similarly, we can give this definition as the operational definition of u1 of t. So we can say u1 of t is just a function that satisfies dx dt equal to x of t convoluted with u1 of t. And we can derive a whole bunch of property from here. So say you do some integration and do some change of variable, then we can get that integration of u1 of t will be 0. Okay? And that fits the intuition of the picture here. So if you take an integration of this thing from minus infinity to plus infinity, then you get 1 over triangle here, and get a minus 1 over triangle here, and then you get 0. Okay. And yeah, and there are more properties that you can get by looking at this problem set 2.96. Okay. And yeah, so those properties tell you that you can just define your u1 function, this unit doublet u1 function operationally this way. Okay. And so those are derivative of delta function. And on the other hand, we can also think about the integrals of delta function. Okay, and now those are not singularity functions. Those functions are actually well defined. Okay, and so the first example of those integrations of the delta function is the unit step function. Okay, and they are useful just like a derivative of the delta function. So before we were listing those derivatives of the delta function give us or characterize the assistance that's the derivative of your input. And so similarly, those integration of delta function will give us will characterize the system as an integration of input. So you think about the system as an integrator. So the output is your input integrated from -infinity to t. And so for this system, and once again you can easily show this is LTI. And I guess we already know that its impulse response is u of t. Okay, but anyway, we can do the calculation again. So u of t, so u of t will be the impulse response of this system, which is equal to integration of delta of t. Okay. And so before we were seeing that you do this integration is 0 until t equals 0, and it's 1 when t is greater or equal to 0. Okay. So u of t, this is a very well-defined function, is the integration of delta of t. And so we also see that is unit impulse response of the integrator. Okay, and then we can think about this as the operational definition of u of t being that x of t convoluted with u of t just be equal to this integration of x of t. Okay, and then just like when we do derivative, we can do higher order derivative. When we do integration, we can also do higher order integration. That's just we do integration more times. So we can integrate our x with dummy variable sigma and integrate to tau. Then this result function of tau. Then we integrate tau to t. Okay, so we can have y being this twice integration of x of t. Then we can define this unit impulse response is integration twice. So we call it u minus 2 of t. Okay. And this function, we call it a unit ramp function, and the result is like it will look like this. Okay, and you can see that why it's called a unit ramp function, because it's ramping up. So at t equals, starting from t equals 0, it keeps ramping up with a unit slope equal to 1. Okay, so this is a unit ramp function, and and then just like before, is doing integration twice. So it's actually equal to the unit step function convoluted with itself. So it's just like our derivation of u2. Okay? So I guess let's try to go back here. Okay. And before we have this derivation of u2 equal to u1 convoluted with u1. And here we have this u minus 2 equal to u convoluted with u. So it's a similar argument. So because you do integration twice, it's applying it's like applying the integration system twice. And anyway, so u is this unit step function. It's a very well defined function, and its convolution is also very well defined. And then you do this convolution integration, then you see that is tu of t, and so it's the slope function cut off at t equal to 0. Okay. And then we can also have the operational definition of u2 being that x of t convoluted with u2 is this twice integration of twice integration of x of t. And so you can generalize this to k, and we find out that you can write this u sub minus k of t being u of t convoluted. It's unit step function convoluted k times, and they are all not singular, so they are all very straightforward function. In fact, they are like this monomial. It's just t to the k minus 1 divided by k minus 1 factorial and times u of t. and they will represent this integration system. So integrate your system k times. Then if you convolute your system, you convolute your input with u sub minus k of t, then the output will be the input integrated k times. Okay, and then finally we have something very interesting to say. That you might already notice that we have weird notation u sub minus k here. It looks a lot like those u sub k before. And indeed that comes from integration is the negation of integration is the negation of integration. Sorry, integration is the negation of derivative. And so this u sub minus k is kind of like the negation of u sub k in the following sense. So first we need to define two things, okay? So it's a bit of funny, okay? So to make everything with a unified notation, we can define all the u sub some number with this. So the delta function, the thing we start with is u sub 0, okay? And then we have u sub 0, and then we have the really weird definition being this u of t equal to u sub minus 1. Okay, I think this is a bit counterintuitive, but this is how it makes sense, because u of t is the unit impulse response to integration twice. So we think about, so delta of t is you convolute it with, okay, so I guess I should write this back again. So delta of t equal to u0 of t, because x of t convoluted with delta of t equal to x of t, right? So we are now thinking about what happened when we convoluted our input with this u sub something function. Okay, so delta is 0 because you convolute your function. Sorry, I should write x of t. Okay, because you convoluted with delta of t, nothing happened. Okay, so x of t convoluted with delta of t equal to x of t, and nothing happened. And they convoluted with u1, you get a derivative, and you convoluted with u minus 1, you get an integration. Okay, so u equal to u minus 1. Okay, and then we can have this really interesting equation says that okay, so before we already know that you have a positive k, positive u convoluted with positive e. So I guess before, let me see, where was that? Probably here. Oh, yeah, here. So from here, we already see that u sub k is u1 convoluted k times, and you can easily see here that you have some k1, u sub k1. So maybe right here. So from here, you have that u sub k1 convoluted with u sub k2, that should be just equal to u sub k1 plus k2, right? And so this is for positive k. And also go back to here. Then we have that from here, then you see that for negative k, we have that u sub minus k1, u sub minus k2 convoluted together is u sub minus k1 minus k2. And but now we see that we also see that we can combine the positive and the negative one, because u sub minus 1 convoluted with u sub 1 will equal to 0, and this can be calculated here by using a definition of u sub u sub 1. So u sub 1 is the unit doublet, and we know that anything convoluted with the unit doublet is its derivative. So, and the u sub minus 1, as we see here, is u of t, and this is du of t dt, and we know it's delta of t, and delta of t is u0 of t. And so you see the minus 1 and the plus 1 and cancel out, actually cancel out, so we have that u sub k convoluted with u sub r of t equal to u sub k over r of t, and this is for every k and r. So every integer k and r. So they can be either positive, negative, or 0. and with 0 being delta function and -1 being u of t. Okay, and yeah, so this finish our introduction on all the derivatives and integrations of the delta function. You see that they have this very nice property that you convolute them together, then this subscript just add together. Okay, and here are more properties that you can remind yourself. So yeah, so those are some properties of delta function, and we have the definition of the unit doublet and singularity functions and the integration function. I guess those should be the rank functions and its generalizations. Okay, and this actually, so there are still a lot of slides, but this actually finish most we want to talk about in chapter 2. So next we will just go through very quickly and want to talk a little bit about chapter 3. Okay, because we are a bit behind schedule. So first is a multi-dimensional case. So you can generalize what we talk about a TI system to a multi-dimensional case where your variable, you have a more independent variable. So instead of u of t, x of t, and y of t, you have t1 to tn, t1 to tn, and you can define LTI similarly. So linearity is still this summation and time delay, and for time invariant, you want the same time delay. You want the time delay on every dimension, etc. Okay, and you can similarly write a convolution for the multi-dimensional system, etc., and analyze your multi-dimensional system. And I guess a good example of multi-dimensional system is the image. So you can look at your image as a two-dimensional system. So this is a discrete two-dimensional system. And you can do a LTI system that kind of calculate the boundary of your image. So say you have an image here that's kind of a black spot in the middle, and you can have a LTI system that calculate the difference between the blocks, and that'll give you the edge of your system, edge of the image. Okay, and think about support, etc. Okay, and then there are a bit of so now it's a bit of review of the delay system we talked about. So we have those delay systems. So it's just convoluted with delta of t minus t0, then you will delay by t0, and if t0 is negative, you actually get advanced. And we see there are differentiation systems characterized by this unit doublet signal we talked about. So x convoluted with u1 get dx dt. And similarly, you have a different system. In the discrete case, that's specified by this actually not this delta of n minus delta of n minus 1, and this is not singular, it's just a difference of two delta function. And we have integration, accumulation, etc. And then you can have edge detection system where your h of n has some property that detect the variance of your system. And I guess skip the detail, and the result will be kind of like this. So you can have edge detection system where input like this, and the output will told you that you have the positive edge here and the negative edge here. And then you have more signal without noise, then you see that it's kind of noisy here. Okay, you can have a different edge detection, and then you can try to smooth out your edge detection with by basically averaging more area. Then you will have more smooth out edge in this input signal. And then when your input has noise, then your output will be also more smooth out, and you see that it's less noisy here because you smooth out more things in your edge detection. And you have a two-dimensional case of edge detection, and the result is that you have an input image with those vegetables, and then you see that you have those output edges that kind of line out the edge of your vegetables like this. Okay. and you can also have a smoother system. Basically average out your signal. So your h of n is this averaging thing. So 1 over something, 1 over some constant for some area, and then you have input signal with those noise, then your output signal will be smoothed out. Okay, and yeah, so that's a 5-minute review of some system that you can build with LTI system. I guess some example of LTI system, and I guess let's try to go to the next chapter, and let's go to chapter 3. Okay, chapter 3. Let's go to more analysis of LTI system. That's Fourier series representation, and I guess so. This is a bit funny. So wait. First 3. This is annoying. Let me try. Sorry. Let me try to change the slide a little bit here. So close chapter 2. And here. And let's go to chapter 3. Hopefully this don't crash the system. Okay. Now it's clear. Slow. Okay. And yeah, chapter 3. So it's a bit funny. So chapter 3 is so now we get our Fourier name here. So chapter 3 is talking about Fourier series representation of a periodic signal. And I guess the end goal of those things is we want to analyze the LTI system. But it's a bit funny. So in this chapter, we actually don't talk about system too much. We are actually just talking about how we decompose our signal. We are going to represent our signal in so-called Fourier series. And in particular, the signal we are analyzing now are periodic signal. And the motivation is that we are going to use this analysis for LTI system. But for now, this is basically, this whole chapter is just a way to decompose our signals. Okay. And yeah, so this is chapter 3. The motivation is for LTI system, but the whole chapter we don't. But later on the chapter we don't talk too much about the systems. We just talk about signals and how to write them in linear combinations. Okay, and but anyway, so for now we still remember the LTI system, and let's look at its motivation. Okay, so why do we want to look at those Fourier series representation? It's because we want to analyze the LTI system better. Okay, and so in particular, we find out that LTI system, because they are linear, they have the so-called eigenfunctions. Okay. And the eigenfunctions are functions that we talk a lot in chapter 1. They are the complex exponentials. It's exp s of t and z to the n. Okay. And we see that, so this is basically what we want to derive today. We see that if the system is LTI, then the function of the phone e to the s of t or z to the n, they are the eigenfunctions of your LTI system, so that I guess we should also call eigensignal, but anyway, we call it eigenfunction. So means that if the input is of the phone e to the s of t, then the output is basically still e to the s of t, but just times another constant, that's h of s. And this big h of s is some function of s that depend on your system. So this depends on your system, and also this s here. So you have different s, you have different history of s. But for now, you think about s, if you just figure s as some constant, then you input some complex exponential e to s of t into this system. Then you see your output is just another constant times e to s of t. And yeah, so this is something very nice because you see that the response of your system to this kind of signal is very easy to calculate. It's just multiplied by another constant. And yeah, so this is basically what we derived today. E to S of t input to any LTI system become big H of S times E to S of t. And similarly for discrete time, we want to change a bit of notation, so we have z to the n, where z is a non-complex number. Output will be h of z to the n. Okay. And this big H of S and the big H of Z are very important things. Very important function of S and Z. And in general, it will be function of complex variable S and Z, obviously. And yeah, and they will be called, okay, so here we have small favorite. And later on, and so this big H is called the system function or system response or transfer function. And we see that you can actually calculate so h of big H of S from H of T. I guess that's kind of obvious because we know small h of T, we know small h totally characterize the system, so obviously they also characterize this big H. But later on we will see that we can calculate also calculate small h from big H. And so big H and small h are very related. And that's why they all are written as this. They are all written with this character H, just small and big. Okay. And yeah. But for now, we focus on this being eigenfunction, eigenvalue, eigenfunction, eigenvalue relation for your system. And it's called eigenfunction because I think it's very similar to what you know in linear algebra. So linear algebra, we have that the eigenequation for matrix. So if you have some linear transformations described by some matrix A, then you have A times some vector V equal to lambda times some vector V. And the V was called eigenvector and the lambda was called eigenvalue. So here is similar. So this e to the st are called eigenfunction, and those big H of S is called eigenvalue. Okay. And yeah, so let's start the derivation. We talk a lot about those equations. Let's first start the derivation to convince you that this eigenvalue equation is true. And so we have any LTI system. Okay, and now we see what happens when we put input e to the st to the system. Okay, and so in the LTI system, from what we learned from last chapter, we know that LTI system is described by the input response small h of t. Okay, and so output will be input converted with h of t. So x of t converted with h of t. And we kind of switch order by the commutative property of convolution. So this is equal to integration of h of tau times x of t minus tau. Okay, and then we just substitute x of t minus tau with our e to the st. Then this is e to the s of t minus tau and the d tau. Then we see that we are very close to finish actually already. So output y of t equal to integration h of tau e to the s of s times t minus tau d tau. And then we just use this property of the exponential. So e to the s of t s times t minus tau equal to e to the st times e to the minus s tau. And basically you look at this thing and think about what thing depends on t. So the only part dependent on t is okay, so maybe let's highlight here. Okay, so the only part that depends on t here is this t here, right? Okay, so and in terms of this decomposition, is this e to the st part. Okay, and then also the nice thing about this is that the integration is on tau. Okay, so the independent variable is t, and the integration is on tau. And so for this integration, e to the st is just a constant, and it can be moved outside of the integral. Okay, so you can write this integration as e to the st integration and the whole bunch of function as tau. Okay, so h of tau e to the minus s tau d tau. And so yeah, so the only part dependent on t is this e to the st, and basically we finish our derivation. So we just need to rename this whole integration. So this whole integration, it depends on, so what are the variable inside? The variable inside are tau and tau and s. But tau is getting integrated, so tau is just a dummy variable. And so this whole thing actually only depends on, I guess it depends on two things. It depends on this function, small h, and it depends on this value s, okay? And anyway, so you can write this just as a function on s, because tau is integrated out, it doesn't depend on tau. So this whole integration, we call it a function of s, so we call it the big H of s. Okay? And yeah, so the important part here is that big H of s doesn't depend on t. And the only part dependent on t is e to the st, and so we derive what we claimed at the beginning. So y of t equal to big H of s e to the times e to the st. And so in terms of t, this H of s is just some constant. And then, as we said, so this is half of the claim we had before. So we found out that we can calculate this big H of s as from small h of t. So big H of s is this integration of h of tau into the minus s tau d tau. Okay. And yeah, so you can think about this quite straightforward integration. So you have any function small h of t, then you can do this integration. Any function small h of t and then complex value s, and then you can do this integration and find out what's the big H of s. Okay. And yeah, so that's basically what we want to derive. So we see that complex exponentials are eigenfunction of the TI system, and this this H of s is we call is the eigenvalue with for the eigenfunction e to the st. Okay. And I guess we still have some time, and so very similarly you can do the standard derivation for discrete time systems. So for discrete time system, we put the input with z to the n, where z is just any constant value. And then we use discrete convolution to see what's the output y. So output y is the summation k from minus infinity to plus infinity, h of k, x of n minus k. And just as before, we plug in h of n minus k with z to the n. So this is z to the n minus k. And then you see the summation of k part is kind of separated from this z to the n part. So you can write this as z to the n multiplied by this summation k part. And yeah, so once again, this summation k part, you just call it the big H of z. So this is just a function of z. This is independent of n, and it depends on small h and depends on z. Yeah, so similarly, we get this derivation that y of n equal to h of z times z to the n, and h of z can be calculated from, so the big H of z can be calculated from small h of n. The summation k from minus infinity to plus infinity, h of k z to the minus k. And yeah, so z to the n is called the eigenfunction for your discrete LTI system, and h of z is the eigenvalue. Yeah, so here is what we want to say. So LTI system, we derive that any LTI system, we derive that there are eigenfunctions and its associated eigenvalues. So for continuous time, eigenfunction is e to the st, and the eigenvalue is h of s equal to this integration of small h of t multiplied with I guess h of tau multiplied with e to the minus s tau. And then for discrete time, I guess you can still write e to the sn here. But for reasons that will be clear later, we want this notation more. So we write it as z to the n, and z to the n is the eigenfunction, and its eigenvalue is h of z. And yeah, so h of z and this big H of z will equal to, now because they have a different notation for z to the n, the z to the n is different notation from e to the st, so this h of big H and the small h also have a different formula. So big H is small h times z to the minus k and summation over k. And these big H are eigenvalues. And as we spoiled before, they are also called system functions or transfer functions. And I guess we can see one example here. So here we have a very very simple system. Y of t is this time delay system. Y of t equal to x of t minus 3. Okay, and it has a unit impulse response as we see today. H of tau equal to delta of tau minus 3. Okay. And then we try one of those complex exponentials. So when we have x of t is this e to the j2t, so x will equal to j2. Then y of t will be, so we use this formula, we use the direct calculation here. We see that y of t is e to the j2 and t become t minus 3, so j2 t minus 3. And just with this property of the exponent again. So it's e to the j2t times e to the j minus j6. So this 2 times minus 3 equal to minus 6. So minus j6 here. And so we see that the output y of t is the input e to the j2t times another eigenvalue here equal to e to the minus 6j. Okay. And we can check that this check out with our eigenvalue calculation, this integration here. So big H of s should equal to integration of h of tau, so delta of tau minus 3 times e to the minus s tau with s equal to j2. And you do this integration, you see that this integration will say tau equal to 3. So this is e to the minus 3 times I guess here we can not plug in s, we can not plug in s yet. So we see that this integration set tau to 3, so it's e to the minus 3s. And if you put s equal to j2, so then you will have h of j2 equal to h of j2 equal to e to the minus j6. Okay. Okay, with the derivation, and so here is the example of that showing that the two equations here we write is actually true for this very simple system. And to finish our LTI motivation, we see that what we want is linear combination as what we want to calculate is eigenfunctions of LTI system. Is that if you express your input signal as the linear combination of those eigenfunctions, then the output can be calculated easily. Okay, because your LTI system is linear. Okay, and so basically in chapter 2 we write our input signal as this linear combination of delta functions. Okay. And so here I guess here we should write a bit better. So in chapter 2 we have as a summation ak delta of minus k. And so here we say that instead of writing the input signal as a delta function, as a linear combination of delta function, we can write the input signal as here is wrong. We can write the input signal as a linear combination of as e to the sn, or I guess let's just stick with the discrete notation here, right? So here we can write, instead of that, we can write this as a sub z and z to the, like this, some z, okay, for different z. And later we'll see how we parameterize those z, okay. And if we have nothing, but we actually have a continuous time. So that's for discrete time. And for continuous time, never mind. Yeah, and so we kind of see the example for continuous time case. So we see that if we have as we derived before, so for e to the s1t as an input to our LTI system, then the output will be h of s1 into s1t. And then we have e to st, then the output will be h of s2 e to s2t. And e to s3t, output will be e to h of s3 e to s3t. And so if our input is a linear combination of those three things, so we have a1 e to s1, a2 e to s2, and a3 e to s3, then the output can be written really fast. So this is even faster than our convolution expression. So we can just say, well, the output is the same linear combination, just multiplied by those eigenvalues. So it will be a1 and times h of s1 e to s1t, then this thing times a2, and then this thing times a3. Okay, and so that's the motivation of why we want to write our signal in terms of a linear combination of those eigenfunctions, because if you write the input as a linear combination of those eigenfunctions, then the output will be the same linear combination, just with multiply with eigenvalues. Okay, so in general, you write your input as a linear combination of those eigenfunctions, then you can immediately write down the output as the same linear combination, so same ak, and just every term will multiply by those eigenvalue h over sk. Okay. And this current case is similar. If your input is a linear combination of those zk, and then the output will be the same combination of those zk multiplied by h over zk. Yeah. And we can go back to our this very simple system example. So we have that y of t equal to x over t minus 3. And we calculate that h of s equal to e to the minus 3s. And so now we can have a funny input. So x of t equal to cosine 4t and cosine plus cosine 7t. And because the system is really simple, so actually the direct calculation of the output is very easy. So we know that this is a time delay system, so we just change t to t minus 3. So the output should be cosine 4t minus 3 plus cosine 7t minus 3. But we can also do this in the eigenvalue decomposition. Eigenvector decomposition, eigenfunction decomposition way. So we can write cosine as so we use our reverse Euler formula. So we can write cosine as a linear combination of complex exponentials. So this is 40, and so you have a j40, j minus 40, and cosine 70. So e to a j70, e to a j minus j70. And then you can directly write out your y from this decomposition. And so here we have s equal to j4, and so e to a minus 3s. So here s equal to j4, and e to a minus 3s equal to e to a minus j12. And so I guess let's highlight all the h part. Okay, so every term gets multiplied by h of s. So h of s are here, those 4 terms. Okay, and so the first term has s equal to j4, and the second term has the s equal to minus j4, and this has s equal to j7, and this has s equal to minus j7. And then you see that h of s equal to e to the minus 3s, and we calculate that here. And you can also check out this expression, with this expression by doing some by just doing some algebra. And so we basically combine those 2 terms together into a cosine 4t minus 3, and we will combine those 2 terms together to cosine 7t minus 3. yeah, those you use this I guess there are multiple ways to do this, to think about this, but you can think of this as the using reverse order again. Okay, and yeah, so I think we are exactly on time, and so here is the motivation of why we want to write signals in terms of e to the st or d to the n, and yeah, we'll do those kind of things in this chapter. Okay, and it's for periodic signal. Okay, so yeah, see you on Thursday, and we'll talk about this Fourier representation of signals. Okay.
Can I ask about the homework?
Yeah, sure.
For the homework, for the last number, this part.
Let me try to remember what's the homework do. Convolution. Okay, this seems pretty straightforward.
Yeah.
Just a lot of case to do.
I can use Laplace transform for this part.
You can use what? Laplace?
Yes.
Why do you want to use Laplace? I guess you can, but here is